Hello everyone, welcome to this Vizuara AI Labs lecture. Today is a very interesting lecture because today we are going to learn all about adaptive step sizes. In particular, we are going to look at three different methods. The first is momentum, the second is ADA delta, and the third is ADAM. ADAM is right now the default optimizer which is used in all in training most of the machine learning algorithms. But to understand ADAM, we need to go through a sequence. And the one concept which is underlying all of these three methods, momentum, ADA delta, and ADAM, is the concept of running averages. So before coming to running averages and understanding it, let me first motivate why we need adaptive step sizes in the first place. If we have a fixed step size, then it turns out that the gradient descent proceeds in a very slow manner, and it's not the most ideal thing to do. The reason is because in back propagation, at each layer and for every different weight matrix, when we are taking derivatives with respect to the loss, different matrices accumulate together. Um, and the accumulation might be different for different layers. So the step size which works for one layer might not work for another layer. Similarly, the step size which works in one iteration might not work for another iteration. That's why we need to look at step sizes which change with respect to iteration. So these are not fixed step sizes, and that's why they are called as adaptive step sizes. So before we look at how can we change the step size with respect to every iteration, first we need to understand the concept of running averages. And I have seen that so many students find it difficult to understand the concept of adam because they don't understand running averages. It's a very simple concept if you actually understand it. So let me first try to explain it. The concept of running averages. So we start out with a sequence of numbers such as a1, a2, dot 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 an, and the normal average for these numbers is just, so if you look at normal average is just 1 by n a1 plus a2 plus dot 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 an, right? A moving average is an average which changes based on the particular element which we are looking at. So when we look at moving average or running average, it is denoted by a1, a2, dot 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 an. So at every sequence, at every step of this sequence, we will essentially have a running average or a moving average. So let us start with a simple example. Let's say I have, or before that, let me start out with the formula for moving average in the first place. So the formula for the moving average is this: a0, which is the moving average at the first element, is equal to 0, and then at is equal to gamma of a t minus 1 plus 1 minus gamma a t. So this is a small a, which is the element of that particular sequence, a1 a2 dot 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 an, and capital A represents the moving average at a particular time. So you might be noticing that I'm using the term running average and moving average interchangeably. So moving average is a sub case of running average. If this gamma also is a function of time, then it's called a running average. But if gamma is fixed, which we are going to assume for the rest of this lecture, then it's called as a moving average. So let us try to understand what this actually means, because this will show up. Let me draw it in a better manner. This thing which we have written here right now will show up in all of these methods. It will show up in momentum, it will show up in adam as well. So we need to understand what is this moving average and where does this formula really come from. So let us take numbers. So let us take numbers as 1, 2, 3 dot 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 up to 8. So let's say this is my a1, this is my a2 dot dot dot, this is my a8. So let us start calculating these moving averages. A0 is equal to 0. So that is already mentioned. Let us calculate capital A1. So capital A1 is gamma times A0 plus 1 minus gamma times A1. And for now here I am going to say, let's say gamma equal to zero point 0.9. So A1, so capital A1 is 0.9 A0 plus zero point 0.1 A1. Then capital A2 is gamma times A1 plus 1 minus gamma times small a2, which is equal to gamma times zero point 0.9 A0 plus zero point 0.1 A1 plus zero point 0.1 A2, which is equal to, so here we are looking at gamma equal to zero point 0.9, right? So let me actually compute this. So this is zero point 0.9 into A1. And okay, so now a0 is equal to 0 anyway, so this term will go out, this term will go out. So a1 is zero point 0.1 into a1. So then this will be zero point 0.9 into zero point 0.1 a1 plus zero point 0.1 a2, which is equal to 0.09 a1 plus zero point 0.1 a2. And then a3 will be equal to gamma times a2 plus 1 minus gamma small a3, which is equal to zero point 0.9 into 0.09 a1 plus zero point 0.1 into a2 plus zero point 0.1 into a3, which is equal to 0.9 into 0.09 a1 plus 0.9 into 0.1 a2 plus 0.1 into a3. So now I want you to take a look at these running or moving averages. Of course, A0 is equal to 0. A0 is equal to 0, which we have already seen before. Look at A1. A1, so capital A1 just depends on small a1. That's nice. Now capital A2 has contributions of small a1 as well as small a2. So it has contribution of the current element, which is a2, but also of the past element. And what is the contribution of the past element? Since the value of gamma is around zero point 0.9, the contribution of the past element is very small. The contribution of the past element is much less than the contribution of the current element. Let's look at A3. So A3 again has contribution for all three elements, small a1, small a2 and small a3. But as we saw with capital A2, the contribution of a1 and the contribution of small a1 and small a2 is small compared to compared to small a3. So the first understanding which we have is that moving average, it captures the effect of the past as well as the present. Okay, that's the first intuition behind moving average. And the second intuition is that if the value of gamma is very close to 1, if the value of gamma is close to 1, then the present dominates the past. So you can think of it as retaining memory. So you have some memory of the past, and the current moving average has the memory of the past elements. Here you see capital A3 is the current moving average. It has memory of small a1, small a2 as well as small a3. But if gamma is very close to 1, then the past values are given much less preference than the present value. Now let us look if gamma is actually equal to small value. So Now the second case which I'm going to look at here is gamma is equal to zero point 0.1. So I'm just going to write down the answers here. It turns out a0 is 0, which is the same. A1 is zero point 0.9 into small a1. A2 is equal to 0.09 a1 plus zero point 0.9 a2. And then capital A3 is actually equal to zero point 0.1 into zero point 0.1 into 0.9 a1 plus 0.1 into 0.9 a2 plus 0.9 into a3. So one thing which we see compared to uh, if gamma is equal to large is that the current values have much more weightage. So if you look at here, if you look at capital A3, if gamma is equal to zero point 0.9, then the coefficient of small a3 is zero point 0.1. But look at for gamma is equal to zero point 0.1, the coefficient of small a3 is zero point 0.9. So one thing is the same for small gammas as well as for uh, big gammas, that the past, if something is way behind in the past, it carries much less importance. So if you look at the coefficient of a1, it is very small compared to the coefficient of a2, and that's the same for a large gamma as well. So the past carries much less importance than the present, and that is the same for a low gamma as well as a high gamma. But if the gamma is low, then the present carries a much more importance. So the third conclusion uh, is that if gamma is low, uh, if gamma is low, then also the present dominates the past. That is the same. But the contribution of the contribution of the present is much higher than for gamma close to 1. So when you think of moving average, think of the following three things. First, a moving average captures the effect of the past values as well as of the present values. Whatever the value of gamma, as if something is way beyond in the past, then it carries much less importance. And the value of gamma actually decides how much importance the present value has. If the value of gamma is very high, then the present does not carry too much importance. It still dominates the past, but the present values, the coefficients are less. But if gamma is very low, then the present dominates the past much, much more, and the contribution of the present values is way higher. So, the way I think about moving averages is that if we have a sequence of numbers, then a moving average actually takes into account the effect of the present as well as the past, and it is a metric for changing something with respect to time. So let's say there is a quantity such as the loss or the gradient of the loss with respect to it, and that quantity is being changing with respect to time, right? So let me use a different color. So at time t is equal to 1, you have this array where there is the gradient value at this time. So let me denote it by this symbol. At time t equal to 2, there is a new gradient value, but you don't discard the original symbol, you just keep it there. And for time t equal to 10, then there are 10 gradient values. So instead of using the gradient value just at that time, if we use the concept of moving averages, we can take into account the past as well as present. Of course, the present carries much more importance, but we still believe that the old contributions have a lot to teach us and we should not neglect their effects. So if we are at the 10th iteration, let's say, we have computed the gradient at 10 different time points. So using moving averages, we say that don't just take the gradient at the current time, but value the gradient at the past also, because the past has a lot to teach us. That's one way of understanding moving averages. So this concludes the part about moving averages or running averages. After learning about moving or running averages, as has been shown over here, and especially this particular formula, we are now ready to understand the first method of adaptive step sizes, which is called as momentum. Now, the idea of using momentum to speed up gradient descent has been actually existing for the past 30 to 40 years. In fact, the first paper where the momentum idea was introduced was published in Nature Letters, and here you can see October 1986, and this was the paper. It was titled Learning Representations by Propagating Errors, and Geoffrey Hinton was one of the authors on the paper. If you scroll down below, you will see the idea of momentum being introduced over here, equation number 9. It was not called momentum here, I believe, but they called it an exponential decay factor to speed up gradient descent. And for from 1986 to around 2010, I would say, so about 24 years, momentum was very routinely used to speed up gradient descent. Now different techniques are used, but momentum played a crucial role in accelerating gradient descent for a long period of time. So let us understand momentum and how it essentially speeds up gradient descent. So the main advantage of the momentum adaptive step size procedure is that it speeds up the gradient descent. So to motivate the momentum, let us look at this particular example. Okay, let us say this is our loss function uh, which we want to minimize, and let's say this is the local optima, which is O, or let me say O. So point O is the local optima. We want to reach this particular point during gradient descent. So let's say we start here at point A. So initially we'll move in the direction of the steepest descent, which happens to be in this direction. And so let's say we reach point B, then we'll come here, then again we'll move in the direction of steepest descent, which lies here. So you see, we keep on going back and forth, back and forth, back and forth, back and forth like this until we reach the optimum. And that is one of the major drawbacks of gradient descent. We keep on doing this back and forth, back and forth, back and forth, which are also called as oscillations. So these are oscillations in the vertical direction in this particular case, and that's why it takes a long time to reach the optima. Whereas just from visual inspection, we know that from point A to point O, the best path is like this, right? The best path is like this, which is shown by the green line. So we need to minimize these vertical oscillations as much as possible. And this is where the concept or the idea of momentum really comes into the picture. What we will do in momentum is as follows. I'm going to draw uh, these contours again here. So here you can see I'm drawing these contours again. Okay, and let's say I'm starting at point number A here. So the gradient will be in this direction, let's say. Then I'll be going to point number B where the gradient is in this direction. Then I'll be going to point number C where the gradient is in this direction. Now, now let's say I'm at point C here, and instead of moving in the direction just given by point C, instead of moving in the direction just given by point C, which is in the vertical direction, what if I take into account the past directions as well? So what if history matters? So what if I take into account the past directions? So if I take into account the past directions as well, here is what will happen. So at A, this is the direction roughly, which has two components, the horizontal component H and the vertical component V. At B, this is the direction roughly. So at B also, there is this as the horizontal component, and there is this sorry, there is this as the horizontal component in this direction, and there is this as the vertical component. Now if you look at the horizontal components in A and B, let me mark them with a different color. For A, the horizontal component is in this direction, and for B, the horizontal component is in this direction. So the horizontal components would add up together. But look at the vertical components. The vertical component for A is in this direction, and for B it is in this direction. So the vertical components of A and B will cancel out together, and only the horizontal component will survive. What this means is that if we take into account the past directions, we dampen the vertical oscillations. We dampen the vertical oscillations. And what this will mean is that if vertical oscillations are dampened, maybe the direction at point C is more dominated by the horizontal. So we might move in this rather than in the orange direction. That is the main idea here. The main idea of momentum is history matters. We need to take into account the past directions as well, so that in this particular case the vertical oscillations cancel out, the vertical oscillations dampen out, and then only the horizontal direction survives. So hopefully we will move closer towards the local optimum, and this is exactly what happens. It turns out that, so this plot on the left hand side is without momentum, and this plot on the right hand side is with momentum. So now I'm going to plot it with momentum. So with momentum, the vertical oscillations kind of dampen and we reach very quickly to the local optima. So this is much faster than without momentum on the left hand side. And while speaking or while writing here, you see I have written take into account past directions. This is where the concept of moving averages is applied, because remember, in moving average we capture the effect of past as well as the present, right? So let me show you how the concept of moving average comes into the picture here. For that I will need to write down the update rule for momentum. So in gradient descent, the update rule looks something like this: Wt is equal to Wt minus 1 minus step size times gradient of j with respect to W at or for Wt minus 1. This is normal gradient descent. But in normal gradient descent, only the gradient at the current time is seen. So this will be modified and this needs to be replaced with the running average. By that, what I mean is that, let's say when we are at the current time t or t minus 1, we actually have the gradient at time t minus 1. We also have the gradient at time t minus 2, dot dot dot. We also have the gradient at time 1. So in momentum, we take into account all of these gradients. Whereas in normal gradient descent, you just take into account the gradient at the current time t minus 1. So the update rule for momentum will look something like this: Wt is Wt minus 1 minus the step size into some sort of a moving average. So now if I want to find the moving average of the gradient, what do I need to do? Let's look at how we found the moving average here. So if we want to find the moving average, first we need to denote a new quantity. We need to introduce a parameter gamma, and then that's it. We'll use this same formula here. So let's say I first construct a new quantity which is V, capital V, which is the moving average of the gradient, is gamma times capital V t minus 1 plus 1 minus gamma times gradient of J for Wt minus 1. Um, that's it. So this is the moving average. This is the moving average of the gradient. And this will be replaced over here. So then the formula for the exact update rule for the momentum looks like this. You first start with the moving average as 0, then you define the moving average as this, plus 1 minus gamma times gradient of j wt minus 1, and then you update the weights. So then you say wt is wt minus 1 minus a step size times vt. This is the momentum update rule. If you think about it, it's actually exactly same as the gradient descent rule, except that for in, uh, in spite or as a replacement to the gradient, we have a moving average. So instead of a gradient which was here, which was fixed at that particular time, we have a moving average, and that moving average takes into account the effect of all the prior gradients so that the vertical oscillations actually dampen out. This is the main idea behind the momentum. And as you can see, there are two parameters which have been introduced here. There is a gamma parameter and there is a step size uh, eta parameter. So it turns out that in momentum, the actual value of gamma which is used ranges from zero point 0.8 to 0.99. And remember what we saw for high gamma values in the moving average. If the gamma value is actually high, then uh, more emphasis is given to the past values than the present values compared to when gamma is low. And why are we giving more importance to the past values? We are giving more importance to the past values because we want to learn from the past. We want the past gradients to cancel out so that only the gradient in the horizontal direction kind of survives. Remember that in the moving average, the present values do carry an importance, but the gamma values controls whether, like, how much importance the present values carry. So if gamma is very close to 1, then still present values carry an importance, but past dominates a lot compared to when gamma is low. So if we want the past to have more importance, then we need gamma to be high, and that is exactly what we are doing over here. So this is the main update rule of the momentum, which really speeds up the gradient descent procedure. And that's why we taught you the concept of moving average, so that you will understand that why the past matters and how to retain the influence of the past gradients. Remember, you can control the influence of the past with the gamma values, and that's why we have high gamma values here, because we want to learn more from the past. So see you in the next lecture.